can be very tricky. It's only probably explicit in a very low dimensional space. And then, when we want to really solve a high dimensional problem, we're going to introduce a number of approximation techniques, right? So here are the two main class of such as approximation. We went over the best approximation already, which actually leads to an algorithm called the loopy belief propagation. And just to remember this take-home message, this approximation amounts to replacing this guy, the entropy of the original distribution, with the best entropy, which is defined only on the singleton and the pairwise potential. Okay, it is exact if the model itself is a tree model. Therefore, you only have the singleton and the pairwise potential defined on the tree. But if you have a more generic model, this is no longer going to be exact. It is actually not even a bound of this because it could be higher and lower than that. And then we also approximate the solution space, the marginal polytope, by an outer bound of that, which is a space of such distributions whose pairwise and the singleton marginals satisfy the local consistency property, right? Therefore, it is by definition bigger than the original space. So today we are going to change the gear and try another approximation, which is arguably simpler and better behaving, although not necessarily better in quality, which is known as the mean field method. So what is mean field? The main idea is to now, again, do something with that hard to compute conjugate function of the partition function, the entropy, and also the operation space. So here we are going to choose first of all a subgraph F, which is used to define a subset of all possible distributions that we have to search for. Okay, and we're going to confine our space of distribution to be that this subgraph is extremely simple in terms of inducing conditional independence properties. Okay, and as a result, your marginal polytope or your solution space, this M, will be actually the space such that this mean equivalence is going to be defined only on the parameters that is feasible for this subspace of distribution, which is a simpler family of distribution. And we can see a few examples later on. And by definition, you are excluding many distributions that is originally valid. Therefore, you are going to have an inner approximation of that. Okay, these are fully feasible distribution, but just simpler, as contrast to the original best free distribution, where a best free approximation, where you just care about certain potential functions that is realized by some distribution where you satisfy local consistency. And there may be invalid distribution which is not globally consistent, but they can still produce locally consistent pairwise and singleton marginals. Therefore, in that case, you have an outer approximation, and here you have an inner approximation. Okay, and then you are going to solve the problem with this redefined objective, and in this now smaller solution space. And in this case, there is one other differences in terms of the loss function. In here, this A, which is the entropy function on that distribution, is going to be exact because we already made sure that this distribution is going to be consistent with a subgraph, which are simpler. Therefore, we made the subgraph such that their distribution are very easy to compute. Their operations, such as entropy, can be very easy to deal with. Okay, and then here we have an exact loss function, no approximation introduced here. Okay, in terms of the computing of the entropy, and then here is a subspace. Okay, and there are a number of virtues in this because now you have a closed form expression of this. You actually can characterize that in terms of whether it is a upper bound or lower bound of the loss function or not, instead of in the best free energy case, you actually don't have a closed form in here, in terms of the original distribution. Okay. So now let's look at a specific example, okay, how this approximation can look like. So here we have this original graphic model. Imagine it is an Ising model, a macro-random field model with all feasible parameters. Okay, it's actually defined in a very high-level way. It means that the entire space of theta such that the log partition function is upper bounded. That's basically all valid distributions. And we know that computing any expectation on potential using this original distribution can be very hard because it's equivalent to doing inference. And we know that doing inference on an arbitrary graph model is hard. Right? But what about a subgraph like this? So here is a subgraph in which the coefficients correspond to the weights of the edge will be all 0. Therefore, it is a completely disconnected graph. So what does that translate to in terms of defining a distribution? So here we have a full distribution, x1 all the way to n equal to some form, right? It's basically some form of theta times t of x, which is the sufficient statistic. In this case, and by the way, this one can be factorizable or may be hard to factorize because of a joint partition function. So here you have this, right? So they are not fully factorizable. But in this case, how the distribution look like? It's actually going to be look like one of equal to this one. It is a single marginal already. Of course, with unknown parameterization, let's call it maybe gamma. Okay, you don't know how to parameterize that, but the form at least look like a singleton marginal of unknown concentration or parameter. And obviously, this distribution is very easy to handle. You can do anything about that. For example, computing the entropy of this is just the sum of singleton entropy, right? Or you can be a little bit more sophisticated by constraining the subgraph to be just a tree by removing some of the edges. You have this intuition that the more edges you remove, the more kind of different the resultant approximation to the original one. But you kind of have a control, right? Here, it might be a better compromise between approximating the true one but versus the simplicity of the computing. So in this case, you have a subset of theta such that some edges are set 0 and some are still retained. So in any case, you are going to now approximate this original distribution with some simpler form, and these are the definition of the mean parameter, but now they exist in such a subspace. Okay, for example, in the case of a fully factored distribution in here, that means all the marginals are become independent. That means you only need to satisfy this condition, which is this mu. In here, I call them tau, which is actually this guy. Okay, to be something that is normalizable, right, between 0 and 1. And then this is another condition, meaning that the joint, this corresponds to the joint probability, P of xi and xj, just equal to the product of xi and xj. Because I removed all the edges already. Therefore, any marginal over a pair equals to the product of the corresponding two singletons, right? And this is a much easier constraint than the original marginal polytope. And you can verify to yourself that this actually leads to an inner approximation geometrically. And then as a result of this, you can also compute in exact form the entropy function. And at the end of the day, you have a much easier problem, okay, which is only a function over the Cartesian product space of 0 and 1 in m dimension, and you are going to just optimize this loss function, okay, over all the possible mu's, which is the singleton marginal. Okay, so here the pairwise marginal disappears because it is merely a product of two singleton marginals. Okay, and this one we know how to do it. It is just the sum of all singleton entropy, and then you know how to solve that, right? This is a small constraint. You bring them in with a Lagrange multiplier, and then you do the right derivation, setting the gradient to 0, and so on and so forth. At the end of the day, you will get this update equation, good for every mu. Okay? And this update equation is sometimes known as the mean field updates, or sometimes it is also known as a mean field message. Okay? Because basically it is about replacing all the neighboring nodes of a node of interest by their expectation. Okay, it is the mean of a previous estimation. This T corresponds to the neighborhood of S. Therefore, you are basically living in the field created by the mean value of the neighboring nodes. That's why it's called mean field. And so this is a very simple algorithm that allows you to solve a inference problem. The inference problem could be A of theta or the mu of every variable, and now you have it. And this loss function also has some nice property. For example, it is giving you the lower bound of the log partition function. Okay, and it can be simply derived from here, right? Because one way to talk about optimization is to maybe minimize the difference between your approximating distribution to the original, as we talked about in our earlier lecture. And this guy is actually correspond to the first half of this equation. Okay, and we know that KL between any pair of distribution is always a quantity bigger than 0 or equal to 0. Therefore, this guy is greater than 0. And now you move this one. On the other hand, you will see that this guy will be a lower bound, okay, of this log partition function. So that's actually a nice property because you are guaranteed to make sense. If you, for example, do a maximum likelihood learning of the parameter given data, log partition function corresponds to actually the likelihood of the data. Therefore, you are actually maximizing the likelihood of the data. Right? So these are mean field approximation, and this is a visualization of the solution space, okay, the feasibility space of the mean parameters. As I mentioned, it is an inner approximation. Why? Because we know that the original space is a marginal polytope, and the extreme points are actually those sufficient statistic, right, in the original model. And they are all realizable even in our mean field approximation. Therefore, they must be in our solution space. They are realizable because you can actually see the definition. A weighted sum of this basically is defining the convex hull of this, and you can make a particular distribution and plug them in, and you can see this actually can be one of the solution to your mu. Okay, and but on the other hand, it is smaller than the original marginal polytope, and the extreme points is also in the solution space. Therefore, they must look like this, right? They're going to exclude some space, but contain the extreme points, and therefore the final shape of this approximation space is looking like this, okay, which we call an inner approximation. So from here, you actually could already see a problem of this technique. Anybody can comment? Originally, we have the best free energy approximation, which is an outer approximation, and they look like this. Right? They look like somehow like a cover outside of that because of the local consistency constraints. They are basically a bunch of half space intersecting and creating a closed marginal polytope, not a marginal polytope anymore, but still a polytope. In this case, you are not necessarily a polytope. Okay, it is like this. So what is the problem with that?
Not a convex space.
It is not a convex space. Okay. Therefore, when we run any iterative method, which is actually by definition a fixed point iteration, which is also by definition a gradient type of method, you may not run into a global optimal solution. Okay. But this is something you have to live with. You get a nice bound as a result of the reformulation, but you lose the global convexity of the problem. So you kind of pay a cost. But still, people like it because it is extremely simple to implement, and it is guaranteed at least to converge to a local consistency point. Okay, because the target is well defined. All right, so that's basically the mean field methods. And now let's take you a little bit further to see how this idea can be broadly applied and with a fair amount of degree of freedom to complex models. Okay, so let's look at maybe a very general graphic model P. Okay, I draw just a graph like this, which in this case it is even a Bayesian network, not a macro random field, just arbitrary graphic model, and I want to do something with the original distribution, and I know it is intractable. Then, for any such distribution, I can always introduce, something called a, product of a cluster marginal, okay, or something called a structured mean field approximation, where you just draw maybe arbitrary clusters on that original graph, okay, and they have to be discrete, okay, for a good reason, because if it is discrete, then you can always introduce a new approximation to the original, which is written as C of Q of XC. Okay, it's basically a product of all the cluster marginals, and the cluster can be defined by yourself. Okay, and you basically decide to use this as an approximation to that, and you can easily see that the mean field is an extreme of this instance, right? Or an extreme instance of this strategy, where every cluster contains only one node, right? But it doesn't have to be one node. You actually can introduce more. And here you can see the interesting idea already. You can actually somehow get an intuition that the quality of the approximation of this Q to the P can be somehow reflected in the number of edges that you removed in the approximation versus the original one. In the extreme case, you removed all the edges, that creates the mean field approximation, right? In the tree approximation we talked about earlier, you removed some edges, but kept some. And if you remove no edge, then you have the original distribution, right? So here, you can kind of imagine a graph partition strategy where you just remove as few edges as possible, but maintain every unit of cluster to be manageable, meaning that for every Q of XC, you want to make sure that you can do exact inference on that. If it is a singleton, then exact inference is trivial. It's basically writing a singleton marginal. But if this particular cluster contains maybe 10 nodes, in the worst case, you can just run enumeration, right? A table of 10 dimensions is okay, it's doable. Therefore, you can still afford an exact inference. Therefore, you approximate each local family with a exact kind of a marginal computation, and then you are going to multiply all these exact local approximation together to form a global approximation. Okay, so that's kind of the idea behind generalized mean field inference. And there are actually some theorem we proved earlier showing you, how to bound the accuracy as a function of the weight of the edge, in the original graphical model. So here, just to repeat the idea, so we introduced the clustering of the nodes, and then your mean field approximation become product of cluster marginal, and then the mean field free energy can be still computed in closed form because that's amount to the expected energy on the cluster, and also the sum of cluster entropy, not singleton entropy. Okay, they are still doable if you know how to do exact inference within each cluster. So this idea is particularly interesting in actually the nowadays distributed computing environment. Suppose that you have many computers. Okay, you have a really large graphic model with say 1 million nodes, and 2 to the power of 1 million is out of question, for any single machine. But maybe 2 to the 1,000 is doable in a high-end machine. If you have 10 of them, you actually can do a pretty large graphic model just by cutting the graph into 10 pieces and spread them across. Right? So each of these clusters can be handled by a client in the cluster, and then they can do this exact computation of the entropy within the cluster, at least, not over the entire graphic model. And by that, you actually can now afford to approximate the true energy function with this mean field energy function, depending on how much computing resource you actually have. And then you are going to use this as the loss function to actually seek a approximation, an optimal approximation, which is that how this each marginal cluster, cluster marginal should look like. Okay, so that's kind of the idea behind this so-called generalized mean field. You optimize each of the cluster marginal instead of singleton marginal. And again, this idea has been there for a while, in fact, and people empirically do this kind of strategy in many of the early papers in variational inference. And the strategy is very simple. You just write down this in closed form, and then you take a variational differential approach and figure out the closed form solution, or maybe a numerical solution to each of these cluster marginal. But it turns out that if you are willing to take some assumption, say your whole graphical model is an exponential family distribution, and then it turns out that every cluster marginal is actually defined by a canonical form. So to the point that you don't have to do any derivation. It's basically taking this form. Imagine that you have a cluster that is, in the context of many other nodes, and you want to write down the marginal of that, okay? And usually, the way you write down the marginal is to write down the marginal actually conditioning on its Markov blanket. Right, so let's say we don't do that. And this is a typical inference problem. And in the original graph model, you don't know how to do that because you need to now sum over everything in the rest of the graph. But now we are doing this cluster approximation, a cluster mean field approximation. Therefore, you imagine on the neighborhood of this particular cluster of interest, we already know from earlier iteration that their cluster marginal is known already. Therefore, you have a P1, Q2, Q3, and let's call this a Qi. By the way, this index are the cluster index, not the node index. You know all the neighbor already, you want to do this. And then the computation of the, this conditional of the cluster given the Markov blanket becomes easier because now you can treat as if all the nodes in the Markov blanket are observed. Okay, if they are not observed, you replace them with their expectation. Okay. And that's basically the idea. You do iteratively, by starting a random guess of the configuration of the Markov blanket, and then you compute this particular, cluster marginal, okay, and then you are going to go through the other cluster and do it cyclically. I think I have a graph showing the simulation. So you say, suppose we begin by knowing the cluster marginal of all these other clusters. I don't know this one. You are going to take a message from all the neighbor, and once this one is updated, it is going to send a message to the other nodes. So what the message is sent? The message sent is basically the expectation of these nodes which are neighboring this particular other cluster. Okay, and once the other one gets the updates, it is going to send messages to the other thing. This is the typical mean field message. You just replace the random variable of interest with their expectation, and therefore they become known, and then you can write down a distribution that is conditioning on these messages. It is a little bit harder to understand without an example, so let's do an example. By the way, there's a theorem showing that this is, after all, a coordinate descent algorithm. It's going to guarantee convergence. But let's look at the example, okay? That helps you to understand this idea, which is very simple. So again, we have this naive mean field problem. Originally, I used this technique that writes down the approximate loss function and the constraint, and then I say take the derivative and introduce a Lagrangian, and then you're going to get updated equation mu equals to a sigmoid function of something else. Right? That's by derivation. So here I have a derivation-free, actually, strategy to get that update, which is the following. So here is your original Boltzmann distribution, which is defined by the singleton and the pairwise potential. And then here is the partition function, right? So this is the true distribution. And I say I want to approximate this by this guy, by a product. I think here is a round thing, a product of all these Qs. And I don't know how the Q look like. Then according to the theorem I just presented before, I know that it must take the following shape. It is going to be, this Q of I, okay, will be proportional to actually the P of I under the original distribution given its Markov blanket. Okay, then what does that mean? It really means that it corresponds to, P of xi and P of MB of I, the joint distribution of the node and also its Markov blanket, then normalized by the Markov blanket, right? Normalized basically by the P of X MB. Isn't that true? Right. So then what is this? The joint distribution of a node and also its Markov blanket. Well, according to definition in here, it only could contain those nodes that is itself and also any other nodes that is neighboring this one. So in the graph, you have this one and all the other one which is in the Markov blanket, and they are weighted by the corresponding edge in here. Therefore, here, and I have a partition function that is not necessarily easy, necessarily explicit. We can just put it there. Then I have a generic expression of this guy in this form. Okay. If I knew the true distribution, I'm going to write the conditional of this guy in this generic form. It is universally true if I know the true distribution, right? So here, of course, the problem is that you don't actually know this value either. These are all hidden variables. Therefore, in the mean field approximation, I'm going to replace them with their expectation. Okay, I just assume they are known. And where do I get this? Well, because in my earlier iteration, I already know the marginal distribution of all these other nodes already, right? So using those those QJs, I'm going to now compute the QI. And once the QI is known, okay, I get all these messages, I'm going to be able to send messages out to other nodes, right? So again, this one is, again, the mean message, okay, the mean field message. And all you need basically are a collection of such singleton expectation computed from all the other QJs. So that's basically, you can see, we don't need to worry about the form of this singleton marginal Q. Okay, it is just explicit from the original conditional distribution of the node of interest given their neighbor. However they look like, you just copy it down and replace all the other nodes with their expectation. You will see actually a more powerful utility of this strategy in many of the later models I'm going to talk about, especially the topic model, where inference can be tricky, but I will make it very easy down the road. Okay, so that's one example. And another inspiration from this technique is that this approximation really can go to more complex approximations, right? So in this case, you are going to now compute this marginal cluster marginal, right? So say this cluster marginal. Then the Markov blanket of this guy is this one, this one, this one, this one, this one, or this. Maybe not this one. This one, there isn't an edge, right? So, and okay, originally you should write down P of this guy, okay, given all the other four nodes, okay? And you don't know the value, but now you can replace them basically with all their expectations. Okay, the expectation come from where? Well, from this cluster marginal, that cluster marginal I got from earlier iterations. Therefore, the same equation applies to a bigger approximation. You can go this big, that big as you can afford, basically, in computing this singleton marginal. Okay, so what makes the difference? So this singleton marginal can be computed from, this singleton expectation can be computed from a singleton marginal, which is supposedly a poor approximation to the true marginal. But it also can be computed from a cluster marginal of different sizes. If you compute this guy from the true distribution, say I compute this guy from P of X, that's basically meaning that this cluster is going to the entire graph. Then you have an exact calculation of the expectation, right? But if I go into smaller, you get a worse and worse approximation, but you have an interpolation from the best to the worst, right? That gives you the kind of flexibility of controlling the accuracy at a cost of computing. Because the reason we don't do this is because I need to sum over all the other variables except this one, which is expensive. But in this case, I need to sum over all the other nodes in this cluster except this one, which is smaller, fewer numbers. And here I have even fewer. And in this case, you have just one to sum over, right? So that's kind of the idea. You have this full spectrum of computational complexity, but as a result, you gain by actually better and better accuracy up to exact inference if you made the cluster as big as the original graph. Okay. So here are some experiments showing you actually this growing accuracy and also the time that you need to spend, on the computation. I think here we compared a few algorithms such as, this is a BP, the belief propagation algorithm on this is really bad because, this is a loopy graph. This is a very loopy graph. Therefore, when you do loopy belief propagation, they will find nowhere. They will converge to some very strange place. But if you do a 2x2 mean field approximation, which is this one, or a 4x4 one like this, you get a better and better approximation. And if you can afford to do the whole thing, you get no error. And why we know this graph? Well, that's actually the experiment design. We made the graph. I think here is 8x8, which is actually enough for us to do exact enumeration. So we can actually afford to do exact inference. So we have the true results, and we are comparing the approximating results to the true results to actually assess the accuracy of that. Okay. And here, of course, at the time span, you can imagine for this one, it will be more time consuming than this one. BP is okay. It's not too expensive, but it's not too cheap either. It is kind of somewhere in the middle. Okay. So that gives you a full picture about the flexibility offered by the mean field approximation. You can really control the size of the message. There are similar strategy in BP. You may heard a word called generalized belief propagation, but that one, originally I covered that algorithm in my graphic model class, but now I decided not to. Why? Because that algorithm was very, very rarely practiced. It is quite complicated. And it is mathematically interesting. It also has a good root in the physics literature, but I have to say it is not very useful these days, so I decided to replace them with more interesting material that is being practiced and used. And the same idea applies to many, many graphical models. For example, here, many years before, actually people are talking about the deep neural network. This is already a deep neural network, which I used in one of the experiments in the paper. And again, people know that doing deep neural network inference is very difficult, right? You have to partition or to distribute it. So how to distribute? I think people right now, by default, doing the distribution by taking layer by layer, right? And again, in the domain of applied world, the computer vision or speech, all they care is this empirical performance at the end of the day, how good you classify and how good you decode the sound wave. But it is not about a quality of mathematical approximation quality. For example, what if you know the latent variable in the deep network? How good your approximation is getting there? People don't know that. So in here we have a simulation study. We create a sigmoid multi-layer deep neural network. And we actually made the size such that we can barely afford it using a very big computer. And then we're going to try different partition. Partition correspond to different generalized mean field approximation. And here, we actually experiment on a layer-wide partition versus a block-wide partition. And you can see the accuracy is actually quite dramatically different, right? So here is the accuracy on the block approximation. This is the accuracy on the layer approximation. And this is the accuracy on belief propagation. So why is that? Hopefully, you can tell why this one gets you a better approximation. Yes, it is removing fewer edges. You can actually see that, right? When you are cutting this layer out, wow, it is the holy grail of deep neural network. You want to make multiple layers, yet your approximation is removing all of that. So it is kind of counterintuitive that you build a model which are supposed to be connected, and then your approximation is to remove all that. And then in the end of the day, you actually don't know what you get, right? So in this case, it is trying to keep at least the edges you originally meant to add. Okay, it is removing maybe the locational effect. Maybe this edge is not reaching too far into the other end of the network, but still within the region it is there, right? And as a result, you get a much better approximation. So this experiment actually gives you some kind of inspiration or some insight into how, if you have a distributed system, to cut graphic models into pieces and do the approximate inference. It is not a random act, but it's not necessarily a quantitative science. You can just visualize the graph and then get a good sense about how it should be cut, right? So I have many examples, such as this factorial HMM. Again, there's a famous paper by Zubin Garmani talking about how to do approximate inference. And he, again, introduced two approximations. One is to do this approximation, basically cutting them into different layers. And the other is to do this horizontal partition, make them into different chains. And you can actually grow them into single chains, multiple chains, and more chains, depending on how your computational unit can afford. right, depending on your distributed resource. And here we have, again, a spectrum of performance comparison showing you verify basically the intuitive understanding that the more edges you retain, the better accuracy you can get. Okay, so that's kind of the message I want to send you in generalized belief mean field approximation. This idea has been practiced intuitively by many people, but now it's becoming, in my opinion, more kind of attractive because of the distributed machine learning era. You have now very many machines, and you may want to play with a very big model. Do you want to keep the single model in the memory of a single machine, or do you want to grow your model even bigger so that a piece of the model can stay in a single machine and you can actually handle a bigger model? Well, this is at least a mathematically principled way of guiding you how to cut the model into pieces. Okay, of course, you want to realize that this partition is not a permanent divorce of all these pieces, because it is an iterative algorithm. When you update this piece, you are actually using messages from other pieces to compute it, and it is iteratively updating until convergence. Therefore, the different modules do communicate. Okay, so that means in a distributed environment, you have to make sure some simulations are made rather than they don't communicate to become embarrassing parallel. Right? So that's the kind of trade-off. And so I have a few slides just to showcase this idea. But with that, I want to move on to actually now talk about a fancy model that we probably all heard about, which is the topic model. But before I do that, do we have any question remaining regarding the general theory behind variational inference? Yes?
Yeah. I saw previously you give an example about the grid-like graphical model.
Mm-hmm.
It seems because in computer vision, a lot of the graphical models are grid-like.
Mm-hmm.
Are you suggesting that using a block-like
Yes.
inference may be better than belief propagation?
Indeed, yes, I'm exactly suggesting this. Unfortunately, not many people are listening to me. But yeah, so using mean field for Markov field is proven a bad idea. And using belief propagation for MRF is also a very bad idea. Depending on, of course, sometimes if the mean field is having certain patterns in the weights, they are attractive. Repulsive mean field, they are attractive mean field with all these details, sometimes they have a chance to succeed. But generally, it is not a good idea, okay, to use this algorithm. In fact, the generalized mean field gives you a much better chance in getting the right inference. It will be more expensive, but as long as you can afford it, it will give you better results. Right? So yeah, if you are a computer vision guy, you should broadcast this message. I think this is an important lesson that I would like people to take. All right, any other questions? And also, likewise for the deep neural network. Okay, I think the deep neural network community isn't really, drawing any advantage on the theory of approximate inference in getting their approximation better. I think most people are following a kind of a heuristic intuition to cut the models or to distribute the data, which is computationally okay. But if you talk about the accuracy, I don't know what's going on, basically. I think people are talking about the deep neural network being unanalyzable, okay, being mysterious, and that's part of the reason, because you don't know what you are approximating at this point.
What's repulsive and attractive?
Oh, repulsive and attractive is coming from the physical literature. If the weight is a positive one, then you call them repulsive. If the weights are negative, you call them attractive. Basically, it is to encourage whether the neighboring states are aligned or anti-aligned.
So the ground truth is attractive. Okay.
Yeah. And they have different implications on how consistent the neighboring nodes can be, and what is the consequence of cutting that edge away. Yeah. Other questions? All right. So if no questions, let's spend some time on this fancy kind of development in natural language processing domain, a topic model. There are a lot of controversy over this model. I'm not in a position to actually defend or argue for this model. I'm just going to present you what the model is and how to deal with that. Okay. Right, so obviously the goal is to be able to handle this problem, to help this lady to handle all the documents that she has. And so let's go through the roadmap of how to actually start such a inference task. Say your boss gave you, say, oh, I have 1 billion documents, do something so that I can do something. I can visualize them, I can make predictions, so on and so forth. Then how do you start with? I kind of learned along the way to approach problem like this using a systematic kind of strategy, starting from understanding what task is. Some people actually don't even understand what task is before they even start a model. It's just very often, but I want to make sure we are not in that category. And then you want to make sure that what your data look like, and how do you want to keep the data formality and representation. And then you introduce the model, you define the inference and learning on that, and you evaluate. I'm going to spend time on evaluation if I do have time, because this is also an important task ignored, in fact, by many machine learning researchers and also practitioners. So I'm going to gloss over this part very quickly because we actually know how to do it already from all our lectures. Okay. Right, so the task, of course, the most intuitive one is to be able to represent this document in some form of vector so that we can measure distances, we can cluster them out, so on and so forth. And the simplest possible vector is, of course, just a word count vector. You do nothing, just count a word, right? But people probably realize that it's not a good idea because they are too high-dimensional and too, too uninformative and so on. So that's one task. There may be other tasks, such as a corpus-wide kind of summarization of the whole thing. Say how many topics are represented, and here is a possible outcome that you summarize the whole thing into 4 topics, and you express every topic in terms of the most frequent keywords, right? And how the whole thing evolves over time. How do you use them to suggest to user most interesting articles and so on. So these are basically the potential applications. So now let's see how our data look like so that such a application can be enabled. So this is a data, how they look like. Obviously, if I give you this, you really want to make them at least standardized. For example, if I give you another document, these 2 things should be comparable, right? Therefore, you cannot just linearize this whole thing and put them into a chain of words and then have another chain of words. These 2 chains cannot be compared. They don't have even a equal length yet. Right? So we want to turn them into representation, and one of the representation is called the bag of word. You just throw them into a bag with their counts. You can also do higher order language model like bigram or kgrams with a better cost. And that leads you to a vector already, right? Of course, in many cases, this is too sparse a vector because the vocabulary can be 1 million, but only a few hundreds of them gets used in a document. Therefore, this vector is highly ineffective. And therefore, we want to maybe build the representation based on the actual semantics instead of just the bare word appearances. And by the way, there are many other reasons for the bare bone word being not a good idea because the word may be synonyms and polysemy, and there are many other phenomena which prevent the word to be interpreted correctly. So here is a possible way of model semantics. I'm just suggesting an idea, and let's see how we mathematically encode this idea. So this is always this thought process. You first suggest some kind of a process that is mathematically encapsulatable, and then you're going to put a math on top of it. So how about we talk about the article like this? That's hopefully mimicking a particular researcher. So this article, after I read it, if you want me to summarize it, I may say, well, this guy is maybe about MT, machine translation in most cases. There may be some content covering syntax. Maybe there are even some machine learning thing. Okay. Now you ask why I draw this conclusion, right? I think the reason I draw this conclusion is because I saw some interesting words. For example, I saw this word blue, which is a very, very common score used in machine translation. Therefore, I conclude it is probably machine translation. And I even see somewhere, a word, I don't know, model, for example. Okay, the model probably is more often used in machine learning literature and all that. So I basically say, I have these 3 topics, and the reason I call them a topic is because they have all these interesting keywords. Okay, that's the first degree approximation to summarization. I may want to be a little bit more kind of quantitative. I say, well, this guy is maybe 60% about MT, 30% of syntax, and 10% about learning. Okay, so that's kind of a typical legitimate way of saying something about the article. Okay, now we give some names, okay, to make them mathematically a little bit more elegant. Yes?
So here you're assuming you know what topics can be.
Oh, no, I don't know. I just imagine, I have a knowledge in my brain, okay? Yes, so in essence, I know there is this word machine translation, which should have been covered by certain things, right? But even if I do not know, I can make them as a random variable, and that's actually the good kind of property of machine learning. You put a placeholder there, and later it will be filled by data, basically, right? So here I'm going to name these placeholders. I call this guy the mixing proportion because they are really mixing up all possible source of topics or contents. Then I call this thing topics, okay? And I want to probably be a little bit more quantitative by introducing something called a unigram, which is the frequency of each word, just rather than just a listing, because obviously there are some words which are more frequent, right? And this actually is the precursor of a topic model, okay? And once you have this, now you can give a shorthand of this article, this long article, just by a vector of 3 dimensions. And then suddenly all your different documents can be compared, right? So this idea actually has been played a lot in the literature, in the community of community of natural language processing. And the key idea is really to kind of do some embedding, right? You have this unstructured document collection, and you want to, some kind of put them as a coordinate in some space called topic space. Okay, in here I call this particular space a topic simplex because I want each vector to be a probabilistic vector of numbers and then sum to 1. Therefore, their space must be a simplex. But they could be other space. It could be Euclidean space where the topic weights can be negative. That's also fine, right? And then, of course, we have some structured topic representation, which could be connected to tell you what topics are represented in this whole corpus. And then I also have this so-called word simplex, which basically is a space of how topic can be represented. Say the topic of sports must be a point in some word simplex where certain words are taking certain frequency and so on. Right? So that's the kind of algebra we need to facilitate if we want to really turn what I just did into a mathematical framework. And before the topic model that I'm going to talk about, there actually are a lot of approaches doing that already. But you can obviously see that what I just described looks like an embedding problem, okay, of high-dimensional data into a low-dimensional space. And such thing can be done by just matrix factorization. And they have a fancier name in NLP called latent semantic indexing, in which you build a document term matrix, and then you do a decomposition, and you get something called a word topic matrix, in which you have every column correspond to the weights of all the words under a particular context. You could call them just topic. Although the number here are not probabilistic, they can be negative numbers, they can be any weights, and you have a document now represented as a vector in such a space. The topic model that I'm going to talk about is actually quite akin to this one, except that now you are modeling not just the word document matrix, you are actually modeling the probability, the likelihood of the data, which are the bag of word representation of the words. And then here you have probabilistic distributions of the words under each topic. And here you have a probabilistic vector of every document, which is that the mixing vector of every document. Okay. So that's kind of the high-level picture people start to think about in the late 90s, and that leads to the following model. Okay, so here I'm going to skip the detail. There are virtues about that. For example, here every row here corresponds to a word, and this word now has a number of different weights under different topic. That gives you an intuitive kind of representation of the polysemy phenomenon. Every word may have different meanings and a different context, such as what I show here. The short can have all these following meanings depending on in which topic. This might be a medical topic, that might be a sports topic. This could be an entertainment topic, right? So the word can take on different weights. And likewise, you can imagine similar political kind of definitions of a word. Even the same idea can apply to image and all that. So now let's see how to do statistics on that. I want to introduce a concept, in statistical model, which will be very useful, called the admixture model. So we all know what is a mixture model already, right? The mixture model means that you have an entity, say a point, say I have an x, and I say this x may come from multiple different mixture components, different Gaussians, and every one of them has a weight. That's kind of the mixture model. And you can do the same actually to topic. For example, this x could be just a word vector. Therefore, you can now cluster the word or the document using a mixture model. But this is kind of naive because that's not, at least in the generative sense, you are suggesting every document being coming from is one of the single cluster, even though you don't know which of them. The resultant uncertainty of the estimation can give you weights of this document from different cluster, but it is the measurement of uncertainty, not the measurement of belonging to different clusters. So we're going to change the idea in here. Here we have a document here, and you have now x, which is coming from a list of words. We're going to enforce the following. We're going to say for each word in this particular vector, it is actually coming from multiple different components. Not the entire thing coming from different components, but every element in that is coming from different components. So this double hedging thing is making another layer of mixture, and therefore we call them admixture. And the construction is like you have the mixture components, but now the mixture components are over distributions of elements, not over distributions of the entire thing, documents. So here you can imagine this is a topic of a particular word distribution. That's a second topic of another word distribution. And then what you do is to define every document to be described by a vector of weights from all these different bins, different topics. So this is called the mixing vector, but this mixing vector is different from what we see in the mixture model. In the mixture model, we don't have a mixing vector. We have a mixture indicator for every component. Then this mixing weights is shared across the entire data set. So remember, in the mixture model, you have every cluster having a weight, and that weight is is used to model all the documents. In here, I'm assuming every document has their own mixing vector. So the first one may have this breakdown, the second one may have this breakdown, and then I'm going to use this document-specific mixing vector to create every document based on all these different topics. And the creation is best described by actually this one. Let me have a graphic model. So this is a graphic model, underlying the topic model, which actually tells you a story. So now I see this word, which are the only data, in my documents, and I have n of them, nd of them. That this document had n words, and I'm going to imagine they are created by an admixture model, as I just said, in the following way. So for this d's document, I have actually the theta d, which is the mixing proportion vector. I'm going to first draw it from a prior. Imagine that I have a prior distribution of the topical breakdown. And I draw it first. And then I'm going to create an article in the following sense. I'm going to create that article word by word. For every word I'm going to generate, I first ask which topic this word is coming from. Therefore, I'm attributing a topic indicator in here. And this topic indicator is going to be sampled from this topic mixing vector, which is unique to the document. And I sample it, of course, n times, n being the length of the document. So now you have every word a word indicator coming from a multinomial defined by theta. And then after you draw the theta, say this particular first word determined by z to be of topic sports. Then I'm going to draw the word for that first place based on the sports topic. So here I have this collection of coefficients, beta, which are the topic-specific word frequency. if I decide a topic to be the first one, then I'm going to use the first vector beta. Beta vector in here are a number of different vectors. I'm going to use the first one, which defines a particular frequency spectrum of the words. I'm going to create a word like that.
So does beta depend on Z?
Beta are the parameters in the model. Okay, they are basically a database of topic-specific word frequencies. The use of the beta will be dependent on Z. You are going to choose which one to use because there are many, many betas. Okay, I have in my collection maybe 1,000 topics. Okay, this word can come from any one of these 1,000 topics, and therefore that Z is going to decide which topic to choose from. Okay, so that's basically the magic thing to allow now a document to bear multiple topical facets, and then every word will be a realization of such a topic strengths in the document. Okay, and this is very different from a mixture model where the entire word vector can be only drawn once from one of the mixture components. Here you are really drawing, the whole thing, n times, and at each time in this document, you are going to have a chance to switch between different topics. Okay, and that gives you a lot of flexibility, and that's why people like this model. And also, it's kind of fun to tell a story like this. It's very easy to tell a story, right? Even though no one believes a real document is generated like this, but it is close to. You can imagine a chimp may generate a topic like a document like this if he doesn't really understand the linguistic, the grammars. Right? So there are no grammar in here. There are only semantics and the data, no grammar. Okay, in this case, yeah.
What restriction is imposed on the drawing of topics one after the other? Like, do you want to restrict it only to a few number of topics, which is what you want to do for a document?
No, there is no restriction. In this case, you could make a restriction, but in this case, here beta is a matrix. Each column is a topic-specific word vector, and the dimension of this matrix is like a D. For example, you have D topics. Then this theta is a D-dimensional vector, giving you the probability of any possible topics that this document could have. And by sampling D theta from the prior, you have a control. If you really believe that some topics are implausible, then the prior can be skewed in a certain way so that that probability can be low. Okay, and here you can see I didn't present you the authentic topic model because over there is a uninformable prior, meaning that every topic is equally likely. I resort to randomness to generate the thing in here. But in here, I'm giving you a very, very ambiguous prior, which can be anything. And therefore, you are supposed to provide the prior in whatever way you want to allow richness in the modeling. For example, this prior can be itself a mixture model, right? And you can have multimodal distribution in here, mixture of Gaussian, mixture of other things. It's up to you. Okay. And again, that shows you the power of at least in a graphical model design setting, you can design anything you want. At the end of the day, you pay a cost in inference. Some inference are easy, some are more expensive. Okay. Are we clear about the semantics, the design of the topic model? This slide is crucial, okay, for you to be able to understand the topic models. Yeah.
So every document has their own theta.
Every document has its own theta, yes. Okay.
And the prior is a distribution over topic distribution.
The prior is the distribution over the topic proportion breakdowns, yes. Other questions? Those people who feel very comfortable with such a diagram can actually design arbitrary fancy graphic models where I'm going to have a slide at the end of the lecture showing you how people can go crazy and put all the plates, all the ingredients on top of that to make them, political ideology specific, to make them network compatible, to make them joining image and text and all sorts of things. But it's about putting more errors and more bubbles into this whole thing. Okay, that's it. All right. And I mentioned that you have the freedom of designing fancy priors. And here, the original, topic model known as the latent Dirichlet allocation is basically using a Dirichlet prior, which is like this, symmetric. You have a limited power in controlling the distribution, in terms of biasing on what particular topic and, unlike what kind of coupling what pair of topic. And later, people introduced some fancier prior, such as a logistic normal, which if I have time, I will cover, but otherwise I will skip, which give you some additional modeling power so that multiple topics can co-occur, can be coupled, and so on and so forth. Okay, that's the model part. And oh yeah, actually I have a slide about the logistic normal topic model, which is kind of cool to know. Okay, so let me spend a few seconds on that. So this theta, we said is a multinomial vector, right? It's basically a vector of probabilistic numbers. Well, by definition, the conjugated prior of a multinomial is Dirichlet. And the reason we use Dirichlet because we can write a pretty clean posterior, okay, given the words and given that it's all a Dirichlet. But you lose some power. You can find out why we lose power by reading, for example, these two papers, okay, and this graph actually gives you some implication already. But suppose we want a richer one. In fact, you don't have a lot of space to introduce richer one because this theta is so restricted. It must be a multinomial vector. Otherwise, you cannot use it to draw topics. Right? So here is one idea. Even though the theta itself is very rigid, how about the log of theta? Okay, and we can actually have a transformation in which we model instead of theta, but a other auxiliary random variable gamma. Okay, we call the gamma to be a pre-topic weight, which can be of arbitrary value, can be 0, negative, anything, and therefore it actually comes from a normal distribution, or maybe from even a mixture of normal distribution, all that. And the reason for that being a good, maybe an interesting alternative is that now you have covariance matrix. In the Dirichlet, you don't have covariance. In here, you have covariance. Therefore, multiple dimensions can have interesting interplay, right? But the consequence is that this guy gamma cannot be used to draw Z because it is not a multinomial vector. Then what you can do is to use this exponential transformation, okay, to push them into a multinomial vector just by exponentiating each one and then divide the sum of that into by this. Therefore, you normalize it. This transformation actually makes a very strange distribution that is called the logistic normal. Okay. Of course, the cost is that you have this very ugly normalization constant in the logistic normal, which can be very difficult to deal with, and the whole thing become non-conjugate, and you are going to pay a cost later on when you do inference. But anyway, let's forego that problem for a while, and let's quickly go over how to do inference on that. Okay. Again, we are going to reuse all the ingredients we learned so far on variational inference. So this is the graphic model now, sitting flat, on its side. You have the prior, the topic proportion vector, and the topic indicator, or sometimes called in assignments. And this is the observed data, and this is the beta, which is the topic. And the whole problem of inference learning is to figure out all these unshaded random variables, right? And if you done things right, you will get for every word an assignment of the word into a certain topic. You have this proportion being correctly estimated. You have the beta being correctly estimated as well. So the point is how to do that. First of all, can you imagine how complex this inference problem can be? Or maybe you think it's very easy. So that's actually an exercise we want to go over a little bit. For every joint probabilistic model and a graphical model, and the first thing you do, of course, is to be able to write down the joint likelihood of the data, complete likelihood. So this is the complete likelihood. You just multiply everything together, and this is the typical Bayesian network factorization rule. You just place everything together, right, with a proper kind of conditional distributions, right? So these are the distribution you need. You have a lot of sub-indices, okay, to indicate, under a collection of choices, which one to be selected due to your choice of the word topic and so on. So by inspecting this one, you may realize that computing a posterior or computing data likelihood can be very difficult. Why? Because here, if you look at only though it looks as if you have only 4 variables, but each of them actually is a huge high-dimensional vector, right? The theta for every document could be, k-dimensional, but there are many documents. And the z is actually 1 per word. That's even more crazy, right? And at the end of the day, you need to sum over all the configurations of beta, theta, and z, and leave only the w's alone. And that actually corresponds to a huge integration plus summation in the super exponential space. Okay, just give you a flavor. This is how it looks like. It looks like this, very, very ugly. Multiple integrations, multiple summations, and it is definitely out of a question that we can compute it. Right. All right. So what should we do? That's the good question to ask. Right. So here are the history of all inference algorithms. People tried either successfully or unsuccessfully on topic models. And there are two mainstream algorithms that are still effectively used. And they have all these competing pros and cons. And today we're going to mention a few words about the variational inference. And actually, mainly I'm going to talk about the mean field. The other ones start to be, actually the third one is also a mean field inference for a special type of topic model. But the second one is a different mean variational approximation, which is no longer used very often. Again, too complicated, even though it is quite good. And we're going to talk about the Markov-Chain-Markov methods in some later lectures. And again, this one is an important method we're going to run into very often in the future. So what is the main idea behind a mean field approximation? That's the main idea, right? We talked about this original joint distribution being extremely difficult to deal with because the partition function is impossible to compute, and this guy also contains many, many coupled terms. Right? And the simplest mean field is to just put every singleton into its own marginal distribution. Okay, so I have this gigantic product of everything you can imagine. Okay, in the random in the model. So every single topic, every single mixing vector, every single word assignment will be its own a marginal distribution. I'm going to approximate this guy with this massive product. So you can imagine it's a very, very poor approximation. All the original dependencies you introduced into the model become all lost. But on the other hand, it's very simple to iterate over this, like the mean field. So people like it anyway. Okay, and I don't advocate the quality of this algorithm, but it is very effective, nowadays in the practical world. So how to write down the form of every singleton? That's the question. Say we actually care about this. We also care about the Q of Z and the Q of beta, everything, right? So how do we do that? That's the question. This is not a slide I actually meant to show because this is from a particular paper who probably did not appreciate the generalized mean field framework. Therefore, they decided to derive the thing on their own, okay, with a few pages of thing, and at the end of the day, end up like this. But now I can tell you that I don't want to do the derivation at all. I just want to use the generalized mean field theory. So here, for example, I want to ask what is a theta. Okay, and remember we say that the theta will be proportional p of theta given its Markov blanket. What is that? It is going to be alpha and z, right? All the z's and alpha. And then you can imagine this is going to be proportional to the joint of theta and alpha and z, right? And then it is going to be equal to the product of theta given alpha and z given theta, right? And then it is going to be what? This guy is a Dirichlet of alpha. And this guy will be a multinomial of z, right? These are conjugate priors and the likelihood function. And at the end of the day, they are going to lead to a Dirichlet of theta given some what? Some alpha and some counts of z, right? That's basically all we went through. Okay, now the question is that we don't know the z. Z are hidden variables, right? We don't actually know that. And here, I'll assume everything is observed. How to deal with that? Well, the mean field idea tells you that if you have any random variable in the neighborhood that you don't know, you'll replace them with expectation, right? Where do you get expectation? Well, in our whole business, we're talking about the mean field approximate to every singleton random variable. Therefore, at some place, you already have it here. Okay, if you don't have it, random guess it. right? And then you are going to iterate these three things cyclically, and use the other two to update the other one. And the formula here is automatic. You don't need to do any reformulation. Okay, you just replace the original counts with their expectation. And that's basically what I liked about the generalized mean field theory. As long as you are trying, you are fine with staying in the conjugate prior family to make the whole thing generalized linear model, then you'll get this for free. All the forms are extremely simple. Just replace the sufficient statistics with their expectation. Okay? And then you iterate and you get a convergence. That's give you one algorithm. This is the whole thing of the algorithm. You start by some random initialization. You need to initialize somewhere. And then you're going to visit every of these singleton marginals, okay, conditioning on the other thing that you need, and then you update until convergence. So very, very simple algorithm. That's why the mean field approximation here is quite popular. People really liked it. Up to here, I think I'm almost done with topic model, and I want to skip this. This is a rather complex thing regarding the logistic normal distribution. The problem is that over there, the prior is no longer conjugate. So at the end of the day, you cannot use the trick that I described. But I tell you one idea. If you have something that is looking weird, say having this weird logistic normalized function or something like that, there is one technique that can save you and to bring things back to control, which is what? Which is this something called Laplace approximation. If you want to remember this word, Laplace approximation is a fancy word of Taylor expansion. Okay, so you have a complex function. You are going to now do a Taylor expansion and keep the first order term and keep a second order term, okay, minus of course the expansion point, and ignore all the other higher order terms. You can always do that for arbitrary functions, right? And then the implication of this is very interesting. Now you have the first order, the second order. It makes you feel like you are in a model of Gaussian distribution, because in the Gaussian you have the quadratic term and the first order term. So I'm going to fold this into a Gaussian approximation to the original distribution. Okay, so that's the trick. For details, you can read this paper, and that's a paper we wrote many years ago to deal with this type of approximation. And it is arguably much better in terms of approximate quality than the other one. But anyway, that's not the main message in this particular lecture. I want to spend a few moments, like the last 3 minutes, talking about how to evaluate a model designed like this. You can see this model is quite complicated, right? You have a gigantic model, and then at the end of the day, you don't actually know how good the model is. And then, even if the model is perfect, you need to solve it with approximation, because the model cannot be really exactly solved. Therefore, you need to introduce another layer of approximation. At the end of the day, you are going to use some the result to the customer, and tell them my solution is good. Okay, how do you tell your solution is good? That's the key. Okay, how do you actually know the model may not be good, or how do you debug? What if there is something wrong in your algorithm or in the model, right? So that's where I feel important to kind of tell apart the contribution of the model correctness and the inference algorithm correctness. Many people show topic model like this. So I got this, look, the topic does make sense. I have this game, I have this, film, and I have a book, and they make sense. That's all one can say. They make sense. The second people may also give you a list of 5 topics, which also make sense in their opinion, right? So it's very hard to compare the quality of topic models. Therefore, that's not a formal paradigm to compare, the quality of your results. But here is a different approach. You are going to now do simulation. Okay, you suppose that you know the model. Okay, you believe in this model, and want to make sure at least my inference algorithm does well. Okay, therefore, in this model, you can create the theta, create a beta, and a z, and they can all be presented. For example, this is here actually it's the theta vector for 400 simulation documents. Okay, the word vocabulary is like this. Every topic has this 20 word, color coded, and that's the ground truth of their frequency. Okay, and this is the prior distribution. The goal now is to remove all this information and handle to the algorithm just the artificial documents, and let the inference run and recover this and that and everything, and see how good they recover, right? And here you can see, one algorithm could recover the result like this, the other algorithm could recover the algorithm like this, and now you can visually see which algorithm is better, conditioning on that they are using the same model. Okay. By the way, here, every bar here is this theta vector on a particular document. That's why you'll see 4 or 3 colors, because they have 4 topics. Okay. And also you can do learning by recovering the vocabulary and the word frequency and compare this one with that one. Therefore, you can actually measure a distance, right? So once do that, there is a very little trick you can play. You can actually plot this measure, based on ground truth against the different algorithms. For example, here you can vary the number of topics, 10 topics versus 100 topics, how the inference quality degrade or stay stable. And varying the number of vocabulary size, you can have a small vocabulary, big vocabulary, the number of words per document, that's the amount of information you can get from the data. And then you can see this trend, by comparing, say, variational algorithm A, variational algorithm B, or Gibbs sampling and all that. Okay. So that's something I encourage every student in graphic model class to practice if you want to design a new model and then you want to deploy an inference algorithm on the new model. Because otherwise, when something goes wrong, you actually don't know whether the model is wrong or the algorithm is wrong or it is the intermix of both are wrong. You actually don't know. But in here, you can have a way to dissect contributions of errors. Right? And again, another idea is often seen in paper. It's called perplexity, which is the normalized likelihood of the data, which gives you a quality of the model. Okay, so here, assuming your inference algorithms are doing right, verified here, now it's ready to compare 2 different models. And the good model gives you better perplexity, worse model gives you worse perplexity. Perplexity is not a measure to compare the quality of the inference algorithm. Even though on many papers, people use this to compare algorithms, that's wrong, okay, because it is a likelihood. And then this is something you want to do at last, which is the empirical comparison of the utility. Say, classification accuracy, use the word vector. There can be many reasons that your classification accuracy can go up and down. But it may not tell you whether the model is good or not, the inference accuracy is good or not. But if you already made sure they are all okay, then it is a place for you to compare whether the resultant theta is going to give you a good classification or not. And that's usually where you can clearly assess the quality of a model, okay, whether they're useful or not, whether you want to use a topic model or use a LSI or other alternatives, right? Okay, so this is the graph I promised. Some genius, really mastered the art of writing graphic models. So they put all these little ingredients, to make all kind of amazing utilities of topic models in a much bigger context. And if you are really curious, you can go search for these papers, which I don't actually know what they are doing, honestly. I just copy the graphs. Oh, yeah, because it's such a big space, and I'm sure they are very interesting papers, although. So that's it for variational inferences. And the take-home message, again, is that for exponential family distributions, you can use the convex duality to turn the whole thing into an optimization problem. And then we have various approximation schemes to approximate the marginal polytope and to approximate the entropy function. And the result is you have this different inference algorithms, which offer you, a full spectrum of trade-offs of accuracy, efficiency, easiness of understanding, and so on and so forth. All right, so we successfully reached to a nice conclusion. Happy spring break. I will see you in 2 weeks.